You can also alternatively access from Kaggle. So Kaggle is an online machine learning portal where a lot of benchmark data as well as some privately collected or curated data sets are available. So if you have, you can also make a free registration for Kaggle. So Kaggle is part of Google. So you can just search for Kaggle. So it will open up. This is the online community for machine learning. So you can go inside, you can make a free registration. So you can sign in or register, and you can also search for data sets here. So there are a lot of data sets available here. So there are also groups for computer vision, these NLP and data visualization and so forth. And this UCI machine learning repository is also a nice repository, dataset repository. So this flower classification dataset originally contains 581,000 samples. So that is a humongous dataset, and there are 54 attributes. That means there are 54 features. So it is a 54 dimensional data. The 54 dimensions, it's also huge. And then you have the prediction. So what are these data sets comprises of? So all these 54 attributes they are saying, they are referred to as the cartographic features. What it means is that it is some sort of a geographical features that has been calculated and then it has been recorded. For this specific session, I am not using the complete data set, but what I have done is that I have taken a subset of this forest cover data set, and I have only taken 14,526 samples. The original data set contains 581,000 samples. I purposefully made it small so that we can try out some examples in a reasonable amount of time. This would take a humongous amount of time for the training purpose, because later on I am also going to explain about performing hyperparameter tuning experiments. So that is also a compute intense process. So you can start with this and then you can scale it up. And instead of using 55 columns. So 55 columns means it has 54 features, and another column is what type of tree is dominant in a specific region. So by analyzing certain features, you have to predict what type of a tree is dominant in that specific region. Website where I used to host the data set. So you can download it. So here is a command line utility with which you can download the data set from any URL and you can unzip it. You are downloading a zip file, so you need to unzip that file. So one additional thing I would like to mention here is that in the coding cell, if you start with an exclamation mark, the coding cell expects a Linux command, because Google Colab is running on top of a Linux server. So you have the Linux kernel sitting there. So you can actually execute Linux commands there. So wget is a command line utility to download files from a URL. So you can specify this URL. So this is where the data file is available. So once you download it, you can unzip it. So let me just connect and show you how this works. So let me connect and get a cloud session, and then I will show you how to execute this. What happens when you are executing this? So once you see a tick mark, then it should be fine. So let us go to the left panel here, which shows the data. So this sample underscore data is something that comes by default, but we are not interested in that. We wanted to download this data file and then unzip it. So when you execute this particular cell, what will happen is that it will connect. So now it is connecting to the VisionCog site. It is downloading that file. and then it will unzip it. So if you just go to the left panel, you can see that there is a data.zip file currently available. How did we got this? We got this using this utility, wget. Since this is a zip file, there is no way you can right click or you can extract it here. So you need to extract it using the command line utility again. So this unzip is the Linux term command line utility with which you can unzip this zip file. So now you have this data. So I maintain one data folder for my other advanced machine learning course where I will be using many of these CSV files for my lectures. But from this, we need to use only this tiny cow type CSV file for this particular lecture. So inside the data folder, there is this tiny cow type.csv file which you can access. So if you just double click on the CSV file, you can see what are the various attributes I picked, the elevation, aspect, slope. So I only took 10 attributes. And then if you, there should be some scroll. So here towards the right, you can also see the entire thing. So I'm not able to see where is the scroll here. Okay, so what we need to see is that these are the CSV files and we will be using these attributes to make the prediction. So let me come back to the original file. So we will be parsing this CSV file using the pandas library. So let me just close this. And now what we are going to do is we will import all the necessary scientific libraries like NumPy, Pandas, Matplotlib, and so forth. And then using the pandas, we are reading the CSV file and we have to specify the path of the CSV file. So if you just go here, you know it is inside the data folder. You have to access this tiny cow type of CSV file. This is the subset of the original data set, which is 5,81,000 samples. Here we only have 14,000 samples. And we can, once we have read this, it will store it in its own internal data structure called a data frame. So in this data frame, you can print the first 5 entries. So the first 5 entries, it starts with elevation. If you just scroll it, you will see all these attributes. So these are 10 attributes, and the last one is the cover type. So what is the type of the tree? So it will only give you numbers, but you have to understand what those numbers corresponds to from this particular list. Label starting with 0. But here the label is starting with 1, so we will do a slight modification there. If you do a describe, you type in describe, it will give you the essential descriptive statistics of individual attributes that you are dealing with. So here you can know that you are dealing with 14,526 samples. And what is the minimum and maximum value corresponding to the elevation attribute? What is the minimum and maximum value corresponding to the aspect, slope, and various attributes? So you can look at these information here. So this tells us the standard deviation as well. So if the standard deviation value is high, you can, just by looking at this, you can understand that the data is very sparse. So they are very spread apart, largely spread apart. Here the standard deviation is small, so the point cloud will be very dense, or roughly dense compared to data with high standard deviation. So these are some quick insights that you can understand about the data by looking at these numbers. Especially the standard deviation is a very useful information to understand about how dense or sparse the data are. Here this says it's a very hugely sparse data set. Okay, so now if you just do an info, that will give you a brief description, a high level description of the data set that you're dealing with. So you have elevation aspect, so you have 14,526 samples. And the last field is the cover type. All are 64-bit integer information. These are attributes related with pandas. So if you look at some pandas tutorials, these are some very common when we are dealing with pandas library. So what we have to do now is that we need to separate out the attributes as well as our target from this data set. So these are our attributes. The first 10, starting from 0 to 9, these are our attributes based on which we wanted to make a prediction what is the forest cover type or what is the tree type that is dominant in that particular forest. So what we will do is that from this data frame, cover type data frame, we will drop this cover type and take the remaining things and store it in X. So capital letter X. This is a standard convention, not mandatory to follow, but this is what usually the programming practice is. The input attributes will be stored with capital X and the output is stored in small letter y. These are the ground truth labels because you are doing a supervised training. So from this data frame, drop the cover type and store everything as X. And from the cover type, pick only, from this data frame, pick only this attribute, cover type, and store it in Y. So this dot log, and within this you are specifying a colon operator. These all are something related with NumPy as well as this pandas access. So this comma separation says, look at all the rows, but pick the column corresponding to cover type. That is how you should understand. And we are accessing it by all the implicit index numbers. That is what this dot log means. So this is related with pandas. So now if you look at the shape of X and Y, we know that there are totally 14,526 samples, but X contains 10 attributes. Y, it is a univariate data because it contains only one dimension. So you already know that it has only 14,526 samples. So now you have stored your X and Y separately. And now what you have to do, the practice is to split your data into training and testing because you already have your data X and Y. Here you won't be able to quickly visualize your data because it is a 10-dimensional data. So you cannot visualize it. If you want to visualize, you have to use some dimensionality reduction on this X to visualize. Okay, so the usual practice we have to follow is once you have your data set X and Y, what you have to do is you have to split it into training and testing. So we can call the train test split function defined in scikit-learn's model underscore selection module. So you call that, pass your X and Y. So this is very much similar to what we discussed yesterday. Specify what is your test size. So we are specifying it as 20%, it's 0.2. And we set a random state as some seeding so that every time you run the experiment, you get the same splitting of training and testing so that your experiment is reproducible. By changing this number, you can vary your training and testing data. So every time you run with 42, you get the same test. If you run it with 40, you get another splitting of 80-20 split. And unlike the previous splitting, now we are adding some new attribute here saying stratify is equal to Y. So there is an, so let me just show you that alone. Stratify is equal to Y. It means Y is nothing but our class labels. What we are saying is when you are splitting the data into 80% training and 20% testing, do an unbiased splitting based on the class distribution. So if a specific class, let me explain what you mean by stratified splitting with a bit more simple example. So let us say you have cat images and dog images. You have 100 samples altogether, out of which 60 samples are cat image and 40 samples are dog image. So let us assume that. And now you wanted to split this into 80% training and 20% testing. So let us using this function call, we could split it into 80% training and 20% testing data. And now when you take that 80% training data set, and if you look at what percentage of images are cat and what percentage of images are dog, it will again be 60%, 40%. Roughly, it will be close to 60% and 40% within the training data set. And that will be the case with the testing data. In your testing also, you will have 60% of that as cat and 40% of that as the dog. So what stratified splitting does is that the proportion of the class samples in your original data set and the proportion of the class samples in your split data set should be similar. So that helps us to learn the distribution of the original data set itself, so that you do not introduce any
Sir,
bias.
please clarify, stratify again. I did not get it.
So it is to split it unbiased splitting. So in your original data set, if you have 60% of samples as cat and 40% as dog, after splitting the data set into 80% training and 20% testing, we expect in the split data set also this 60-40 ratio is maintained.
Okay.
Is that clear? So we preserve the proportion of the samples in our split data set as well. If we do that, so for any classification problems, it is recommended that we do a stratified splitting. Otherwise, we will be introducing some bias. We should not get more samples from cat and less samples from dog images. So to avoid that, so whatever your original data set proportion is, we want to preserve that proportion when we split it. So that is what achieved by this stratified splitting. And this is the right practice of splitting your data for classification. For regression, there is no classes. So you only have one particular data set. So there is no need to specify stratified splitting for regression data set. But when you are splitting classification data set, we have to be careful about splitting it using a stratified splitting so that we preserve the proportion of the samples. So this function will throw out 4 metrics. That is, it will take X and split it into 80% training, 20% testing. Y also 80-20 split. So you catch it appropriately with the relevant name so that you will not be confused. So put it like X train X test and Y train Y test so that it is easy not to confuse yourself. So now when you look at the shape of X train and X test, so now it says it is the 80% of 14,564. So that's why you get 11,620. This is 80% training. The remaining 20% is the testing samples. So now you have your training and testing data set. How do we apply this softmax regression for this classification problem? So let us go there. So inside the scikit-learn's linear model module, there is a class called logistic regression. So yesterday we used linear regression for continuous value prediction. So now you have multi-class classification. Theoretically, when we were looking at the lecture, we said that logistic regression is for binary class and softmax regression is for multi-class. That is the theory. But when we come to the scikit-learn library, they don't implement separately logistic regression and softmax regression. They only have one class, which is named logistic regression. But by specifying an additional argument, you can make it behave like a softmax regression. So they just keep it simple. They only have one class, but based on the setting, you can either make it work as a logistic regression for binary class or softmax regression for multi-class. So what is the additional argument that you have to specify? It is this. So you have to specify this argument as multi underscore class is equal to multinomial. If you specify this, it means you are making logistic regression to work as a softmax regression. And when you are solving for the best theta parameters, you have to use this solver as LBFGS. We don't have to actually explicitly provide this because by default, this solver will be taken. Just for the explanation purpose, I am explicitly showing it. but these all are sort of default settings. For multi-class is equal to multinomial, we have to explicitly give. Otherwise, by default, it is for binary classification. So this you have to additionally specify. This LBFGS, why I have shown it here is that this is the numeric optimization algorithm that is approximating the Hessian matrix, the second order derivative matrix for faster convergence of theta parameters. And and here we can, if you want, we can also specify some random seed. This influences the way the theta parameters are randomly initialized. So that is the only purpose there, because we are using gradient descent to solve, because cross entropy do not have a closed form solution. So it definitely will work with gradient descent only. So it will be using cross entropy for multi-class once you set these options. And then we have to create object for this class. Logistic regression is the class. So we specify these arguments so that whenever an object is created, it will instantiate, it will invoke the, what is that function called? Constructor. Inside the class, there will be a constructor. So the constructor, it will take these as arguments and create the object accordingly. So once you have this class, you can call the fit function using your training data set. So you pass your training data set, 80% training data set, and you train your softmax classifier. So here you should assume there are 7 classes and you have 7 set of theta parameters corresponding to each of the class, and then it is trying to make the classification. So that is how we should understand. So what I mean to say is that previously I was showing. So here there will be 7 classes and there will be 7 set of theta parameters. So the probability will be distributed such that you will have 7 probability values. When you sum up them, it will be 1, and you will optimize based on the correct classification is based on picking the highest probability corresponding to the correct class label. So once you train this, after training it, you can call this function score using your testing data set, 20% testing data set. So when you call this score function, what it is trying to calculate is how many of the samples are correctly classified. So this is a simple metric which is saying what percentage of samples are correctly classified. This is not related with confusion matrix or precision record. This is a very simple estimate of, from your testing data set, how many of the samples are correctly classified. So here it says 62.8% of samples are correctly classified by the softmax classifier for this classification problem. Say for example, you wanted to look at what is the class label predicted by our model for the first 10 samples from our testing data set. You can just pass this x test colon 10. It will pick the first 10 samples. This is something related with Python, the slicing operator. So it will pick the first 10 samples, and it will, there is a built-in function called predict. Built-in in the sense it is the member function of the class. So you can access that member function using this dot operator, and you are predicting. So these are the predicted labels. So here you get what are the labels predicted by our model. If you want to look at the actual labels that is present in y_test, so you can print this. I am putting here dot values because this is something related with pandas data frame. So just to display it, I am calling these values. So here you can see the first 3 samples, the class labels are same. That means our model was able to predict the samples correctly. But when you look at the 4th and the 5th sample, we expect the class label is 5 and 7. But what our model predicted is again 1. Both are as 1, class label 1. So that is a misclassification. So that is the reason why we get only 62.8%. I am only showing 10 values, but it is not possible to actually enumerate like this and keep seeing where is the right classification, where is the misclassification, and so forth. So for that, you have to construct the confusion matrix, which is an easier way to look at how many of the samples are correctly classified, how many are wrongly classified, and which class got uh, more misclassification, and so forth. So far, we applied this training straight away. Let us go back to the descriptive statistics that we saw here. And now let us take this attribute elevation. In the elevation, you see the range of the values are like 1861 to 3845, the range of values. But now when you look at the slope attribute, it is within the range 0 to 56. So there is a huge disparity in the range of values between elevation and slope. And if you just scroll it here, you might even see some large values. So here it is something between 0 to 7,173. So there are disparities in the range of values for different attributes. And when we use gradient descent based approach to find the best theta parameters, it is a good practice to bring all the attributes to a similar range, preserving the scale, but bring it to the similar range. So yesterday we looked at two feature scaling techniques. One is called min-max normalization, and the other is called standard scaling, standardization based scaling, where we find the mean and standard deviation, and we sort of push the attributes into a unit normal distribution, the mean 0, standard deviation 1 based distribution. Scikit-learn provides a built-in function to do that scaling. So what you can do is that from the scikit-learn's pre-processing, you can import this class called standard scaler. So as a rule, you can see that when you import something from scikit-learn, if it is starting with an uppercase, it means it is a class. So you have to create an object and manipulate it accordingly. If you look at the train test split function, which we do, so here it is lowercase. It means it is a function. So it will be easier for you to quickly distinguish whether this is a function or it is a class that we are importing. Anything starting with uppercase is a class. Here you can create a object for the standard scaler, and we call a fit function on this x underscore train. So here I wanted to also introduce one more important practice on correct practice when we apply scaling to the data set. You shouldn't perform the scaling on the entire data set, like on the X, you shouldn't do it. You have to split the data set first as X train and X test, and on the X train, which is our 80% training data set, we need to estimate the mean and standard deviation. That's what we should do. And this fit function is estimating the standard deviation and the mean for all the 10 attributes that we have. If you think of it like 10 columns, for the first column, there is a mean and standard deviation. Say, for example, corresponding to the elevation, there is a mean and standard deviation. Corresponding to the aspect, there is a mean and standard deviation. For slope, there is a mean and standard deviation. So for every attribute, that fit function will estimate the mean and standard deviation. That's what the fit function does there. Once that is done, so it will internally store it. And now you have to call a member function called transform corresponding to this object. So you transform, you apply it on x underscore train. So what this transform will do now, So it will apply that standard scaling equation. Like, so what was that equation? Let me just try to do that here. So x prime is equal to, say for example, let's put it capital X. So it is x minus mu. So we have to subtract that mean and then divide it by the standard deviation. So this is the equation, x minus mu by standard deviation. So when you call transform, it will pick for the elevation, there is a mean and standard deviation. It will apply this equation for that. For the slope, there is a mean and standard deviation. It will apply that. So this transform is actually executing this equation for every attribute. So you get the standard scaled version of your attributes for the training data set. So to distinguish that from non-standard scale, I suffix it with underscore std, just to distinguish that it is the standard scaled version. And now for testing also you have to do this transformation. But the interesting thing to notice is that for the 20% testing data set, you should not estimate the mean and standard deviation separately and apply this equation. If you do that, it is wrong. The right thing is whatever mean and standard deviation you estimated for the training data set, you have to use that same mean and standard deviation to transform your testing data set, the 20% testing data set. So now you have both training and testing data set, which is sort of pushed to a unit normal distribution. So it is a standard scaled version now. And now we are going to once again create another softmax regression model. And let us train the model using the standard scaled version and see the performance. So what I'm going to do is I'm going to create another classifier and I suffix it with underscore std to show that it is the standard scaled version for the model. So the remaining everything is the same. And now when you call the fit function, so let me just put it in individual line. Here the fit function, you pass the standard scaled version of your training data set. This is the feature scaling applied. There is no scaling applied to labels or the output because it is called feature scaling. So you only apply that to your input attributes, not to the class labels. And once you have trained the softmax classifier for feature scaled version, now you can look at the score and see the performance of the classification accuracy. So now we can see that it has reached 70% classification accuracy. So just for a comparison, when we trained the model without scaling, we reached only 62.8%. But just by applying that standard scaling, we were able to improve the classification accuracy. So data pre-processing is also an important factor towards the performance improvement of your model. So this here we can straight away see a justification how just by only changing or applying standard scaling, you are able to improve something like 8% classification accuracy. And that is a significant improvement to achieve. And I was talking about this confusion matrix. So there is a functionality provided by scikit-learn to obtain the confusion matrix, which is defined inside this metrics function. So here you can just call this metrics and there is something called plot confusion matrix, and you specify your model and then you specify your testing data set. So here you have the standard scaled testing data set and the label. So here you can see the confusion matrix for various classes. So since you have 7 classes, so it tells you the classification accuracy of these 7 classes. Similarly, you can try it for the standard scaled as well. This will sort of help you understand the classification accuracies. So think that this is the true correct classification. All that along the left to right diagonals, they are correct classifications. And you can see 729 samples belonging to class label 0 is correctly classified. So that is what you should understand from here.